Hey everyone, welcome to This Explainer. I am so excited to have you here today because we're going to take a look at the actual, literal chemical foundation of our green energy future. We're diving into a really fascinating paper from the Chemical Engineering Journal Advances, and it's called Amortizazole-Based Solid Polymer Electrolytes for Next-Gen Multivalent Batteries. Now, okay, I know, that title sounds incredibly dense, but don't worry, we're gonna unpack exactly what that means, how the tech works, and why it is just absolutely crucial for the future of our planet.
So let's start with a big question. What if the battery of the future is actually terrible to build? It's kind of a provocative thought, isn't it? I mean, we all love the idea of a fully renewable energy grid, powered entirely by solar and wind. But there is this hidden reality beneath that whole green promise, and that's the physical manufacturing impact of creating the technology to store all that energy in the first place. Okay, let's dive right into this. Right now, as you probably know, lithium-ion batteries dominate the market. They're in our phones, our cars, and even those early grid-scale storage systems. But that reality comes with some severe drawbacks: resource scarcity, really complex geopolitical supply chain risks, and a shockingly high carbon footprint just to extract and refine the metals. Contrast that with what we actually need, right? A true global renewable energy grid. The absolute bottleneck here is that we desperately need massive, cheap, and reliable energy storage. Lithium simply can't scale cleanly or cheaply enough to meet that global demand forever. We literally need a new chemistry.
Section 1. The multivalent promise and the liquid problem.
To replace lithium, researchers are looking at what they call multivalent metals, specifically calcium and zinc, and on paper, they are perfect. They're super abundant. In fact, calcium is the 5th most abundant element in the Earth's crust, so you're definitely not running out of it anytime soon. They're dirt cheap, and they hold a massive theoretical energy capacity. So you might be wondering, why aren't they everywhere? Well, that brings us to the liquid problem. Traditional batteries use liquid electrolytes to slosh ions back and forth, but calcium and zinc are highly reactive. When you pair them with standard liquid electrolytes, they immediately trigger all these unwanted side reactions. The result? You get these thick, crusty, passivating layers and sharp metal spikes, they're called dendrites, that basically grow and literally pierce and kill the battery right from the inside out. The holy grail to fix this catastrophic failure is something called a solid polymer electrolyte, or an SPE. Instead of using a highly reactive, flammable liquid, an SPE is exactly what it sounds like: a solid, flexible, almost plastic-like matrix. It lets the ions travel safely between the battery's anode and cathode without triggering those nasty dendrites or side reactions. If we can get the SPE right, it's a total game changer. We finally unlock the true, safe potential of calcium and zinc batteries. And as you'll see here, this brilliantly illustrates the core approach the researchers took in this study. They didn't just want to cook up a new SPE in a vacuum. Instead, they used an integrated framework. They combined the laboratory synthesis of new chemical electrolytes with an immediate life cycle assessment, or LCA. They are doing something that is incredibly rare, but so vital. They're testing new chemical solutions for battery performance while simultaneously measuring their environmental cradle-to-gate impact right from day one.
So, what exactly is their brilliant chemical fix? Well, they synthesized a new type of solid electrolyte using a polyaminotriazole, or PAT, base. And the really interesting part here is the use of nitrogen atoms in that base. You see, older polymer designs used oxygen-based ethers, which essentially acted like superglue. They trapped those highly charged calcium and zinc ions. But by using nitrogen-based triazoles instead, the ions can move around much more freely. Plus, they were able to create this at a pretty mild temperature, under 70 degrees Celsius, with fantastic 98 to 99% yields. And finally, they mixed in 10% PTFE. That's basically the exact same Teflon coating you'd find on your favorite nonstick frying pan. They added that to give the material really tough structural integrity and to cut down on electrical resistance.
And when we look under the microscope, we can actually see the physical results of this synthesis. On the left, we've got the zinc integration, and on the right, the calcium. Just look at how incredibly smooth and continuous those surfaces are. There are no visible salt precipitates, no weird phase separations. The metallic salts have integrated perfectly and seamlessly right into that nitrogen-rich polymer matrix.
Section 2. Testing the electrolytes. The lab results. To really grasp the electrochemical results here, I think a traffic analogy works best. Calcium is what chemists like to call a hard acid, and because of that, it forms very tight, rigid bonds with the polymer matrix.
Just imagine a car getting completely bogged down in bumper-to-bumper gridlock traffic. That is calcium trying to move through the electrolyte. Zinc, on the other hand, has borderline acidity. It forms much more labile or flexible bonds, so instead of getting stuck, zinc swiftly hops lanes, jumping from one nitrogen atom to the next, just zipping effortlessly through the matrix.
And the raw data absolutely backs this up. Look at this stark difference in performance. Zinc boasts an ionic conductivity of 0.12 millisiemens per centimeter. Meanwhile, calcium is sitting way back at a sluggish 1.4 times 10 to the negative third millisiemens per centimeter. So zinc is vastly superior to calcium in this specific solid electrolyte system, which effectively proves that its little lane hopping ability makes for a much more efficient flow of energy. Now, the researchers actually tested 3 different chemical variants of their polymer, and one emerged as the undisputed champion. It's called PuCSU, derived from succinyl trial. PuCSU significantly outperformed the other 2 variants they tested, which were PIN and PPH. Why? Well, it turns out that below 400 degrees Celsius, PuCSU has a completely amorphous structure. It doesn't have any rigid crystalline roadblocks built into it, which means it maximizes that ionic flow and boosts overall battery efficiency. Honestly, in the lab, PuCSU is an absolute electrochemical triumph.
Section 3, the plot twist, the life cycle assessment. Okay, here's where things get complicated. The highest performing battery, it's the worst for the environment. Despite PSUC being the total electrochemical champion of the lab, the life cycle assessment, which again measures the cradle-to-gate environmental cost of making these materials, proves that PSUC has the most severe environmental footprint of all the variants they tested. No way around it. Let's break down exactly why that is. The global warming potential, or GWP, of synthesizing PSUC is honestly pretty staggering. We're talking up to 8.1 times 10 to the negative second kilograms of CO2 equivalent per functional unit. And over 80% of that massive carbon footprint comes from just 2 things: the heavy use of a chemical called hydrazine and the sheer amount of electricity required to complete the synthesis.
So, let's look at the other variants to see how this builds out the larger picture. The PIAN and PPHE variants have significantly lower carbon footprints. They also score way better across human toxicity and resource depletion categories. They are undeniably much greener, cleaner materials to produce. But, as we just saw in the lab results, they suffer from inferior electrochemical performance. Basically, they are far better for the planet to make, but they make for considerably worse batteries.
Section 4, the ultimate trade-off. This crucial point is summarized perfectly by the researchers themselves. They noted that their findings are, and I quote, highlighting a trade-off between environmental performance and electrochemical functionality. This is the core tension of the whole study. If we want to successfully build the green grid of tomorrow, material scientists absolutely have to anticipate these sustainability trade-offs at the earliest stages of research, like way before we start mass producing millions of these batteries.
Which leaves us with a lingering, pretty provocative question to close out this explainer. Do we prioritize battery performance, or do we prioritize manufacturing sustainability? Think about it. If the best battery costs the Earth to make, is it still actually green energy? It's a really complex, challenging reality that climate tech innovators have to wrestle with right now. Thank you so much for joining me to explore this fascinating research. I hope it leaves you looking at the battery in your pocket and the grid powering your home just a little bit differently. Keep learning, and I'll catch you next time.